Hello, I'm Haoran from Peking University. The title of the topic is A Tale of Two Sides of Wafer, Physical Implementation and Block Level PPA on FlipFET with Dual-Sided Signals. This is the outline. I will first introduce the so-called FlipFET, which is a brand new emerging technology. Next, I will talk about how to do physical implementation and the backend design framework of the FlipFET. Then, the design results will be given, followed by the conclusions. In this part, I will show you the key features of the FlipFET technology. The advanced logic technology follows two scaling trends. One of them is the functional wafer backside. It started with the backside PDN, with backside signal and backside device on the roadmap. Now moving towards fully functional backside. The other one is the advanced device architecture, moving towards 3D transistor stacking, such as the complementary FET, CFET. The CFET, which features two transistors stacked on each other, both on the wafer front side, could achieve further area scaling beyond the 6-track FinFET or the 5-track nanosheet FET. It has more scaled standard cell designs of 4-track or even 3-track height. However, backside pins are not supported in any of these 3 transistor standard cells due to the limitation of device structure and process complexity. Bridging cells such as the nano TSV are necessary for backside signal routing, which leads to huge area penalty. Moreover, the ultra-scaled CFET standard cell has higher frontside pin density than the non-stacked FET standard cell. This will cause the routing congestion issue. As a solution, we previously proposed a novel transistor architecture called the FlipFET, FFET. The FlipFET is named from its wafer flipping process. The FFET standard cell has pins set inherently on the backside and achieves further 0.5 track scaling beyond the CFET. The FlipFET acts as the first combination of fully functional backside and 3D transistor stacking. The back-to-back stacked NFET and PFET in the FlipFET is a key feature different from the CFET. With symmetric frontside backside signal and power, the FFET standard cell features unique dual-sided inter-cell routing. The backside signals help improve the routability and enables pins inherently on the backside. However, the CFET uses asymmetric standard cell design. This will cause larger cell height and parasitics. Moreover, the CFET is not split gate friendly, and this leads to extra cell area penalty. In this part, I will show you how to realize the physical implementation of the FET, including the dual-sided signal routing and power plan, and its backend design framework. Dual-sided pins push the need of inter-cell routing on both sides. We call this dual-sided signal routing. There are two dual-sided signal routing enablers. The first is the dual-sided input pin, which means each input signal has corresponding pins on both sides. Frontside input or backside input can be chosen for cascading based on the location of the previous stage's output pins. However, this will lead to very high pin density and intra-cell routing failure due to the lack of M0 signal tracks. For example, for the backside layout of the 2.5 track FlipFET AOI22D1 cell, there will be no BM0 signal track for B1's backside input pin or B2's backside input pin due to the BM0 blockage. The second enabler is the dual-sided output pin, which means each output signal has corresponding pins on both sides. Frontside output or backside output can be chosen for cascading based on the location of the next stage's input pins. Considering the output pin number is far less than the input pin number, the dual-sided output pin pattern has much lower pin density on both sides, and thus the M0 signal tracks are enough for intra-cell routing. Therefore, the dual-sided output pin is the more reasonable enabler for the dual-sided signal routing. Here we show the algorithm of the dual-sided signal routing. The right figure shows the example of the input nets n. First, we set the decomposed frontside netlist NF and the backside netlist NB. Then for each net, we initialize two temporary nets, nFront and nBack, with nSource, that is the input pin in the net. For each output pin in nSyncs, we first find its corresponding cell C, and then gets its site type according to the cell library and assign this output pin to nFront or nBack by its site type. Then repeat above and we can assign all the output pins to nFront or nBack. Then we add nFront to nF and nBack to nB. After processing each net, we will get the complete frontside netlist NF and backside netlist NB. At last, dual-side signal routing will be conducted based on the NF and NB independently. In terms of the power plan, there comes a question. The VSS M0 power rails are on the front side, but power bumps are on the backside. How to connect the frontside power rails to the backside PDN? Here comes our solution, the power tap cell, a cell specifically designed to implement this connection. It is placed right above the backside VSS power stripes. Note that the power tap cell is area efficient thanks to its tiny cell area, and it has only limited impact on the utilization. The whole backend design flow for FET begins with the prepared tag files, libraries, and logic synthesis. Then comes the physical implementation, including floor plan, power plan, placement, clock tree synthesis, and dual-sided routing. Then the power performance assessment is conducted with dual-sided RCnet extraction, STA, and so on. At last, we will get the block-level PPA of a FET core design. This part will give the experimental results. We first characterized the standard cell libraries based on a virtual 5nm node PDK. For fair comparison, we used the 3.5-track 2-fin FET and the 4-track 2-fin CFET with the same transistor intrinsic characteristics. The FET outperforms the CFET substantially in terms of timing and power for its smaller parasitics. A 32-bit RISC-V core was conducted as a benchmark design. For both FET and CFET, they are powered by the backside PDN. Note that FM0 and BM0 are only used for intra-cell routing, so they are not included in the count of inter-cell routing layer number. To investigate the maximum advantages provided by dual-sided signal routing in enhancing FET routability, we first used the routing layer up to FM12 and BM12. Compared with the CFET, FET FM12, BM12 achieves higher utilization, thus better routability. The FET achieves distinct core error reduction compared with the CFET. As a contrast, if we use frontside only signal routing in FET, there will be higher pin density compared to the CFET on the front side, and the maximum utilization degrades below CFET's max utilization. So the FET needs dual-sided signal routing to realize its full area scaling potential. Next, we compare the block-level PPA between FET and CFET, both with frontside only signal routing for fair comparison. The FET has much improved power frequency relation and a much higher frequency at the same core area compared with CFET. These advantages are because the FET standard cell libraries has better performance in terms of area, timing, and power. As we mentioned before, the utilization is impacted by the input pin density on each side. As given in the left figure, the input pin location can be flexibly adjusted in a FET standard cell. Through redistributing the input pin, we can modify input pin density on both sides. Besides the benefit of higher utilization, the block level power performance can be improved by distributing the input pins evenly on both sides, as shown in the right figure. This is because the metal parasitics are reduced for the lower interconnect density, which originates from the lower pin density. Furthermore, power performance is compared at equal routing layer number. This gives a fairer comparison at the similar manufacturer cost. The baseline is the FET with frontside only signal routing. The figure below shows the power performance results with various backside input pin density proportions, ranging from 4% to 50%. With input pin distributed evenly on both sides, the FET routed with FM6 BM6 achieves the highest frequency without power degradation. To further decrease the back end of line layer cost in FET, we reduced the routing layer number on both sides simultaneously. The maximum utilization remains a constant value until the routing layer number drops below 4 each side, and the utilization can still reach 7% with only 2 routing layers on both sides. There's almost no power efficiency degradation until the routing layer number drops below 5 on each side. These all validated the great space for cost-friendly design in the FET architecture. So let's make a summary. The FET is a novel stacked transistor technology which combines 3D transistor stacking, backside power and signal, and backside device for the first time. We carried out a full spectrum physical implementation and PPA evaluation framework on the FET, including power plane, dual-sided signal routing, and dual-sided RC net extraction. The FET shows greater scalability in terms of PPA beyond the CFET at both the cell level and the block level. With the flexibility of input pin density distribution and dual-sided signal routing, the FET can be further improved in routability and PPA while keeping the manufacturer cost reasonable. We believe that the FET has great potential as a key enabler for the continuous scaling in the future. Thank you for attention.